All right, I've got 10:20, so let's go ahead and begin. Hopefully you were all able to uh, check out the video that I posted on Wednesday. The video was from at the end of the spring semester back in the spring, and introduced you to some ideas with complex variables, and also introduced you to something called Euler's formula. That's the most important thing to have gotten out of that video. In particular, I went on to look at some complex eigenvalue problems. I'll do some more of that today. But the most important thing to come out of that video is an understanding of what's called the polar form of a complex number. And the polar form of a complex number is intimately related to the formula e to the I theta is cosine theta plus I sine theta. So this is something known as Euler's formula, or Euler's, usually we say Euler's formula. Euler's identity is reserved for something else, but we call that Euler's formula. And so the idea is that you can take any complex number a plus bi, and you can write it in the form r e to the I theta. And this is where r is the modulus of the complex number, which is the square root of a squared plus b squared. So the video went into that and talked about kind of the relationship between this polar form, complex numbers, and then how we're going to use that involving the eigenvalue method. Because the idea is, when you solve for p of lambda, so you have lambda squared minus the trace of the matrix times lambda plus the determinant. This is how we get our characteristic equation. It is a quadratic equation, and so you could end up with eigenvalues that are of the form a plus or minus bi. In other words, a complex conjugate set of eigenvalues. So a complex conjugate pair of eigenvalues. And what we've done in the past is we've said, okay, well, if lambda is a plus or minus bi, then there are two possible solutions here. There's, I'll call it y1, which is e to the a plus bi times t times some vector alpha, and then alpha 1, and then y2, which would be e to the a minus bi times t times some eigenvector alpha 2. But both of those solutions are complex. And so what we talked about in the lecture on Wednesday is, well, really all I have to do is pick one of these. Say I pick this one, and I can take this one, and rather than list a complex solution, I can take this and look at the real part of that solution and the imaginary part of that solution. And both of those are real solutions. And we're going to do an example of that here in just a second, but just reminding you of what that conversation looked like and the importance of Euler's formula to that conversation, because you'll have things like e to the ibt pop up in doing that, and we're going to replace those with cosine theta plus I sine theta. So the two major things to come out of Wednesday's discussion was Euler's formula and the plan for how to attack complex eigenvalue problems by taking one of the complex solutions and splitting it up into its real and imaginary parts. Now, my plan for today is we're going to look at 3 examples. And on each example, I'm going to work the problem with you using the eigenvalue method so we can keep getting practice at that. But then we're going to pause to say, okay, here's the solution. What does that solution look like in the phase plane? What kind of behavior do we have? So we're going to start with this first example. We're going to look at the critical point behavior or the equilibrium point behavior at 0, 0. That's always the equilibrium point for these systems is 0, 0. So what kind of behavior do we expect at 0, 0 exhibited by this system? Then I have a couple of different choices for you, and I'll talk more about the choices as we go along. So let's start with this system and see what we can get into. So our system here is x prime equal negative x minus y prime equal 2x minus 3y. So I've got dy dt equals -1, 2, -3 times y is my system. And this is where y has components x of t and y of t. Okay, with that in mind, I know that my coefficient matrix A is that matrix there. So I'm going to write down my characteristic polynomial. It's lambda squared minus the trace. The trace of that matrix is -4. Remember, the trace is the sum of the diagonal. So -1 plus -3 is -4. And then I'm going to add on the determinant. So the determinant is -1 times -3 minus -1 times 2. So lambda squared plus 4 lambda, and that is 3 plus 5, or 3 plus 2 gives 5. So there's my characteristic equation. It does not factor as much as we would like for it to. It just doesn't. So since this does not factor, I need to use quadratic formula to find the root. So I'm going to set this equal to 0. So lambda is opposite of b plus or minus the square root of b squared minus 4ac all over 2a. This turns out to be -2 plus or minus I once you work through it. So we do have a complex conjugate pair of roots. Now at this point, there's enough information here to actually answer the question that's in Learning Catalytics. But I'm going to go ahead and solve the problem. And then we'll talk about later on this next week, on Monday and Wednesday of next week, how I can simply just look at the eigenvalues and know what kind of behavior we have. So in order to solve this problem, I'm going to do the same thing I've done for the eigenvalue method with you when we were doing real problems. I'm going to look at the matrix A minus lambda I. So I'm going to choose, because I only need one of these, I'm going to choose lambda equal to -2 plus I. This is going back to the point I made in Wednesday's class that you only need one complex solution to generate two real solutions. So I'm going to look at just one of the complex eigenvalues here, not at both of them. So I'm going to choose that as my lambda. I'm then going to subtract it from the coefficient matrix main diagonal, just like we've done previously. So I'm going to look at A minus lambda I. That's the matrix. -1 minus -2 plus I. -1, 2, and -3 minus -2 plus I. So far, none of these steps are different than what we've done previously for real eigenvalue problems, with the exception of I don't need both eigenvalues. I just need one. So this will simplify, and in its simplified form, we have 1 minus I, and we have -1 minus I. So this is our matrix A minus lambda I. Now, with that matrix in tow, what we typically do is we look at A minus lambda I times alpha, where alpha is, let's say, A1, A2, and we set this equal to 0, and we figure out the weights for the columns to make these cancel out. Now, unlike the real eigenvalue problems that we were working on previously, I've got some i's running around here, some complex imaginary. I've got the imaginary number I running around, so it makes it harder to look at the weights that are involved. My recommendation to you is to make one of the weights 1 and then just solve for the other one. So I'm going to pick A1 to be 1, and you could have picked A2 to be 1, either way. So I'm going to pick A1 to be 1. If I look at what the top equation is, it's 1 minus I A1 minus A2 excuse me, 1 minus IA1 minus A2 equals 0. And along the bottom, it's 2A1 minus 1 plus I factored out the negatives there, times A2 equal to 0. So if I let A1 be 1, this is 1 minus I minus A2 equals 0. So that says that A2 is 1 minus I. And you can see that that would also work for down here. If A2 is 1 minus I, you get 2 out of the combination of those two. So one of the variables, basically what I'm saying here is one of the variables is free. So you can freely choose one of the two variables, A1 and A2, because it's a redundant system. And once you freely choose one of the variables, you can solve for the other one. And then what you do at that point is, if it's a little bit messy, remember you can multiply by any scalar value and scale the eigenvector, and it's still an eigenvector, even in the complex case. So with A1 equal to 1 and A2 equal to 1 minus I, the vector alpha, this complex vector, is 1, 1 minus I. So we have our eigenvector. We know the associated eigenvalue. So we know that a complex solution to this problem, which in the notes I typically have referred to this as y sub c for complex, is alpha e to the lambda t. But in this case, it's complex, so it's 1 over 1 minus I e to the negative 2 plus I t. And this is where the conversation from Wednesday's class comes in, because when you have this complex one, we're going to take the real and imaginary parts of it to make the real ones. So in order to do that, I feel like it's the best policy for most students to write this thing out, to separate out first. What I mean by that is write this vector yc as, take the eigenvector, for instance, and you can decompose the vector into its real and imaginary parts. So this top component 1 is really 1 plus 0i, because there is no imaginary part there. But you can see the real vector is 1, 1, and the imaginary part is 0, negative 1. So you would break that first piece up into 1, 1 plus 0, negative 1 times I. So I have rewritten this complex vector as a sum of two real vectors, but the second vector is times I. So this is a vector in the complex plane. And then I'm just taking my properties of exponentials. This is e to the negative 2t times e to the it. And I know from Euler's formula that I can rewrite e to the it as cosine t plus I sine t. That's from Wednesday's class. So this is a nice separated out view of this complex solution. And so once you have the complex solution in that form, what you should do at this point is take the real part and take the imaginary part. And both of those are your real solutions that you'll then have for the original problem. So the real part is the vector that's not multiplied by I. So you see how we took this complex vector here and we separated it into a real vector and an imaginary vector? Well, if I take the product of all of these terms, that's a vector. And I want to know which is the real vector and which is the complex vector. So the real vector here consists of 1, 1 times e to the minus 2t times cosine t. You can see that if you multiply this by this by this, that's all real. But similarly, if I take the imaginary vector 0, negative 1 and multiply it by the sine term, I times I is negative 1, that ends up being a real quantity. So I times I is negative 1, so you would get minus 0, negative 1 e to the minus 2t sine t. So if I was to FOIL all of this out, right? Because you've got two terms here, that would be FOIL. If I was to FOIL all of this out, this would be the two terms that aren't multiplied by the imaginary number I. Similarly, if I look at the imaginary part, it's the part that would be multiplied by I. So you would get 0, -1 times e to the -2t cosine t. That would be multiplied by an I. And then you also get 1, 1 times the sine term. Now, one of the primary mistakes that I see students make when they work through this is they think the imaginary part includes the I. It does not. The imaginary part is only the thing which is multiplied by the I in the expression. So don't include the imaginary number in either one of these solutions. So I'm going to combine this into one vector now. If you read across the top component of the vector, you get e to the -2t cosine t. And if you read along the bottom component, you get e to the -2t cosine t plus sine t. So there is one real solution. And the second real solution vector will be, read across the top, e to the -2t sine t and e to the negative, well, I'll make it e to the -2t negative cosine plus sine. So my solution, real solution to the entire problem, or the general solution, if you will, is that the original problem is a linear combination of the real part of the complex solution plus the imaginary part of the complex solution. So it is a linear combination of those two vectors that I just wrote down. And I'm gonna pull out, since each vector has the e to the -2t term, I'm gonna pull that term out real quick. And there's a reason for that here in just a second. We'll talk about it. But that would be our general solution for this problem. And I don't mind if you want to combine this into one vector, if you want to leave it this way, whatever the case may be. But for what I'm about to talk about, I think it's best to leave it in this form. All right, so here's what I want you to decide. Based on the way that our solution looks here, what kind of behavior can I expect in the phase plane? Can I expect node behavior, saddle behavior, spiraling out, that's the source, or spiraling in toward the origin, or a center? A center is a completely periodic circle or ellipse, so a closed curve in the phase plane. Which of these correctly is the behavior that we're going to see here? Now, you may or may not know this, but you can tell by looking at the solution which one it's going to be. If you understand what the solution is representing geometrically, then you understand which of these is the correct answer. And that's what I'm trying to figure out this morning, is if we understand that or not. So based on this solution, I claim that you can tell me what kind of behavior you're seeing here. All right, you got about 10 seconds. All right, everybody has responded. The majority of the class has picked spiral sink. So let me show you that result. The majority of the class picked spiral sink E, which is correct. So let's explain first off why there's a spiral, and second off why it's sinking toward the origin. So looking at this solution, the vector that I have here and here, so you can think of this as this controls the direction it points in, and the exponential term is going to help control the magnitude. Because it's a scalar component. So as time goes on, what is happening to my direction? The direction that the vector is pointing in the plane. It points to where the point is located at any time. As time goes on, because this vector involves components for both x and y that are periodic, then whatever path the particle is taking, it will repeat that path every 2 pi time, because the directions will be the same over intervals of 2 pi. So from 0 to 2 pi to 4 pi, the direction that's swept out by the changing vector will be exactly the same. The trajectory will be exactly the same. And since everything has the same period here, both vectors have the same period, then a linear combination of the two will sweep out the same path periodically. So if there wasn't something modulating the magnitude of the vectors to change them over time, you would just get a closed curve in the plane, because they would, whatever path the particle takes, it would, or whatever path the object that we're modeling takes in the plane, it would just repeat that path, the point would. The x coordinate and the y coordinate would just repeat their paths identically every multiple of 2 pi. Every integer multiple of 2 pi. But we have this e to the minus 2t term. And that term over time is making the magnitude of this vector smaller. So what you have is a closed circle or a closed path in the phase plane whose magnitude is being drawn in because the vector is decreasing over time. So the spiraling behavior is coming from the fact that these are periodically, you're kind of creating a closed curve in the plane, but it spirals in because the e to the minus 2t term is controlling the magnitude. And so what I want you to understand is this is very much related to the eigenvalue. The eigenvalue here was -2 plus I. So let's think about where each of these parts ended up in the problem. We'll start with the -2. The -2 ended up right here in the final answer. The reason that I knew looking at the eigenvalue that I was going to spiral in is because the real part of lambda being less than 0 indicates that we're going to spiral in over time. So it's a spiral sink. Where does the other value, let's call it b, so this was the imaginary part, 1, where does that show up? Well, you can see here, when I had the vector e to the e to the minus 2 plus it term, right here, this is where the 1 showed up, right? It's right there, understood, but it shows up right there. And when I used Euler's formula, I wrote this as cosine t plus I sine t. If this had been a 3, it would be cosine 3t plus I sine 3t, right? So this 1 that's here is the coefficient of t inside the cosine and sine term. That makes this 1 the angular frequency. So the real part, or excuse me, the imaginary part of the eigenvalue equaling 1 is the angular frequency. So the rotation or spiraling in the plane will have frequency 1 because that value was 1 in the eigenvalue. Now, That's enough to know that it's spiral, that you have a spiral sink. But the follow-up question here that I want to ask is, just because you have a rotation doesn't mean you necessarily know the direction of the rotation. So the follow-up question here is, what direction does the system spiral in towards 0, 0, which is the critical point? Okay, so for this, we need to go back to the original system. The original system was dy dt equal -1, -1, 2, -3. And I don't even need the solution for this. I just simply want to take a look at this coefficient matrix, because what this coefficient matrix does is, for any initial condition, say y of 0 equal to y naught, this is the initial vector in the plane. I can look at the y value at any point in the plane I want and look at what the system is telling me the direction is at that point in the plane. So if I have my phase portrait, which is component plotted against component, so the x component over time plotted versus the y component over time, and I pick an arbitrary point, say I pick 1, 0. So I want to look at what the system is doing to the point 1, 0 in the phase plane. Well, I've chosen what my y naught value is, or my y value is, and all I'm going to do is plug that into the y here and look at what the system does to it. So if I have -1, -1, 2, -3, and I'm operating on an initial starting point of 1, 0, the system tells me, if I multiply that vector times the matrix, that's just going to pick off the first column, because it's 1 times the first column, 0 times the second column. So it's just going to pick off the first column. I'm going to get -1, 2. So this is the direction that the phase plane points in at the point 1, 0. So what direction is that? Well, a vector -1, 2 would be in this direction. And I claim that that's enough to tell you what the rotation is going to be. You have two choices for rotation. You can do clockwise or counterclockwise. And based off just this small piece of information, to the left 1 and up 2 coming out of the point 1, 0, which one is it? Clockwise or counterclockwise?
Counterclockwise.
Yeah, it's definitely going to be counterclockwise. And I can do that for all the other points. Like I could look at 0, 1. 0, 1 would pick off the second column. So if I do -1, -3, 0, 1, that'll pick off the second column. And -1, -3 is to the left 1, down 3. So it's going to look like that. Similarly, if you did 0 or -1, 0, it's going to look like that. And if you did 0, -1, it's going to look like that. So you can see that the rotation that we have here is going to be a spiral around the origin. It's going to spiral into the origin over time. So we have a counterclockwise spiral sink. So that's the kind of language that you should use when answering these questions on the skills quiz, on the Maple Lab, and then for the exam next week. Want to take a look at it in Maple, just to make sure that what we've said is happening actually is what is happening, and also to give you some insight for your Maple Lab stuff. So for this particular problem, we're looking at this first example here. I'm just going to go ahead and enter both ODEs, and then I'm going to do DE plot. and I'm going to plot ODE1 with ODE2. That creates a system. System variables are X and Y. And then I need to give ranges to the different values. I'll say 0 to 10, minus 5 to 5, minus 5 to 5. And I'll go ahead and put in an initial condition or two. X of 0 is 1, Y of 0 is 0. X of 0 is -1, Y of 0 is 0. I don't need many because I'm going to show the arrows anyway. But there is our system. Now, because the real part is 2, the magnitude of this vector is shrinking very, very quickly, right? So e to the minus 2t is decaying very, very rapidly. So I'm not going to see much of a spiral there unless I zoom in. So if I just kind of click on the graph and click on zoom, and I zoom in, as you start to zoom in, you're going to start to see much more of a spiral. You can see how it's going to wrap around the corners, keep wrapping around. It keeps spiraling in. So you've got this sort of spiraling behavior from both sides. It's hard to tell that it's spiraling in if you focus on what it looks like from afar, right? So if you focus on what this looks like here, it's hard to tell the difference between this and a nodal problem, but there is a little bit of bend here. If I had a problem that was on a much smaller interval, then we'd be able to tell it apart pretty well here. So let me shrink this down to a smaller interval so you can see the spiral behavior a little bit better. Then my starting points aren't in view. So I've got to go at least out to 1 and -1. So it is spiraling in a little bit here, but like I said, because the eigenvalue, the real part of the eigenvalue 2 is such a fast decay, you're not seeing it as clearly as you might otherwise. All right, so that is an example of a spiral sink. I have some really good examples of this. There's a Maple file called 2x2 system behaviors or something like that. And you should really read through that file very carefully because I go into every different behavior of these eigenvalue systems, and I have an example of it. It's the perfect companion for working on the Maple Labs that are Maple Labs 5 and 6. All right, let's look at another one and kind of see how we do with it. So in this example, I've just changed the system slightly, same question. I'll work through it, and then you tell me what the behavior is. Right, so our system is x prime equals x minus 2y, y prime equal 5x minus y. So in matrix form, this is 1 minus 2, 5 minus 1. So our characteristic polynomial is lambda squared minus the trace times lambda plus the determinant, which is 1 times -1 minus -2 times 5. So the trace actually disappears here. The sum of the main diagonal is 0. So you don't have a middle term. And then the second term here is -1 plus 10. So that looks like 9. So your eigenvalues here, if I set this equal to 0, you get lambda squared is -9. Lambda is the square root of all of that, plus or minus, which is plus or minus 3i. So I have purely imaginary roots. And so I want to see if you've picked up on the conversation we had with the first example, go ahead and answer the question. You shouldn't need to at this point. You shouldn't need for me to solve it for you to answer the question that's in Learning Catalytics. If you understood what was happening with the first example and what I talked about there for the geometry, then you should know what's going to happen with this example as well. So go ahead and answer the question, and let's see if we're thinking correctly about this morning. So the eigenvalues are plus or minus 3i. All right, you got about 10 seconds. All right, all the results are in. The correct answer is we have a center or a pure closed circle, ellipse, whatever the case may be in the phase plane. To see why that's the case, if we talk about this in the way that we talked about the last example, I know that this is a complex eigenvalue. And complex eigenvalues lead to rotations in the phase plane. You could think of them as spirals if you like, but it's either spirals or centers. Right? So closed circular paths in the phase plane. However, because this is purely imaginary, right? Lambda is 0 plus or minus 3i, then I know that 0 is controlling the magnitude. So there is 0 change in the magnitude between periods. So whatever my solution is going to do over time, there's 0 change in the magnitude between periods because it's going to be modulated by a term that's e to the 0t, which is 1. So the scalar multiple of my complex solution is going to be 1. It's not going to change periodically over time. So whatever it does for the first 2 pi seconds, it'll do for every multiple of 2 pi seconds from then on, because there's nothing to change the magnitude of the vector over time because the real part of lambda was 0. So if the real part of your eigenvalue is 0 and you have a complex eigenvalue, you automatically know the kind of behavior is going to be a center behavior. And then 3 is going to be the frequency of oscillation. The frequency of oscillation here is going to deal more with the not the eccentricity, the how many circles per unit time this thing covers. So imagine a point speeding around this curve in the phase plane. The frequency is going to tell me how fast or slow the point's traveling along the curve. So frequency of oscillation is kind of related to the speed at which the point travels along the curve. Okay, so let's show what the solution is here so we can get one more complex example under our belts and make sure that we're seeing what it is that we're supposed to see. So there's only one case here. So like I said, I'm going to choose lambda equal to 3i. Then a minus 3i I. So I'm subtracting 3i from the diagonal. So here's my matrix. Subtract 3i from the diagonal. So this will be 1 minus 3i and negative 1 minus 3i. And you also have negative 2 and 5. So there's the matrix I'm working with. I need to look at the eigenvector associated with this eigenvalue. So I'm going to take this 1 minus 3i, negative 2, 5, multiplied by a vector a1, a2, set it equal to 0. And I'm just going to choose one of them and solve for the other one. So I'm going to choose a1 to be 1, and I'm going to solve for a2. Okay, so if I choose a1 to be 1, let's look at what the, I'll look at the bottom. It's a little bit easier or no, excuse me, I'm going to look at the top. It's a little bit easier to pull the answer out of the top. So you've got 1 minus 3i times a1 minus 2a2 will be 0. So if a1 is 1, that's 1 minus 3i minus 2a2 is 0. So 1 minus 3i divided by 2 is a2, which means that my vector alpha, my complex eigenvector, is 1 minus 3i divided by 2. I would recommend for the problem that lies ahead, just to make your work a little bit nicer, I would recommend multiplying by 2 so that you're working with better values here and using the vector 1 minus 2, 1 minus 3i. So that's, if I was doing this problem and had in my notes, this is what I would be using as the complex eigenvector here. So my complex solution then is the complex eigenvector times e to the eigenvalue, which is 3it. I'm going to separate this into a real and imaginary vector. So this is 2, 1 plus 0, negative 3. So that's the eigenvector broken up into its real part, 2, 1, and its imaginary part. There's no imaginary part in the top, so it's 0, negative 3. And then e to the 3it, according to Euler's formula, is cosine of 3t plus I sine of 3t. So this going to this is Euler's formula. All right, so if I look at that complex solution, I need to pick out its real and imaginary parts. The real part of that complex solution would be the vector 2, 1 times cosine 3t, and the vector 0, negative 3 times sine 3t. But if I take 0, negative 3 times sine 3t, I'll have I times I, which is negative 1. So I'm going to end up subtracting those. So written out, this is 2 cosine 3t. And then the bottom is cosine 3t plus 3 sine 3t. All right, the imaginary part is going to be, you've got the 0, negative 3 times the cosine, because those are multiplied by an I. So the imaginary part will be 0, negative 3 cosine. And then you also get an imaginary part if you FOIL this out and you take the first term times the last term. So 2, 1 times sine will be multiplied by an I as well. So the other real solution here is 2 sine 3t and minus 3 cosine plus sine. So those are my two real solutions, which means that the general solution here is a linear combination of the real part and the imaginary part of the complex solution, which is C1 times this first vector and C2 times the second vector. All right. And you can clearly see there's no exponential term here. It's missing. I mean, it's there, but it's just e to the 0t because we had no real part for our eigenvalue. So there's nothing that will change the length of these vectors over time. Whatever path the linear combination of these two vectors traces out for 0 to 2 pi, it'll be the exact same path for every multiple 2 pi interval from then on. That's why this is a completely periodic solution. So completely periodic solution. And if you have a periodic solution to a system, that automatically initiates a closed curve in the phase plane. Now, that closed curve doesn't have to be a circle. You can get circles, but you most of the time will get ellipses. So you can get a circle or you can get an ellipse, and the center of the circle and the center of the ellipse turn out to be the origin because that's where your critical point is. That's the point that you're kind of orbiting. So let's take a look at that one in Maple as well. Okay, so we're looking at this system. Let me restart this. ODE1, ODE2, and I can just go up here and copy and paste this in because it's the same command I want to use down here. I'll open this up a little bit more. Whoops, forgot to load my DE tools. So there are your ellipses. Now, one of the things that, let me change one of these to make it look a little bit better. One of the things that you're going to run into when you do the phase portraits of these is Maple doesn't do a great job of giving you smooth, nice looking answers right off the bat. So there are my two spirals, or my two centers. They're both ellipses centered at the origin. You see how it's all jagged? Remember that you can use the step size command. To get smoother looking circles. And you can change using line color what the color of the things are. You can, manipulate the arrows, all that kind of stuff as well. So lots of different options for how to make this look, but you're going to get a center-like behavior here. One of the things that I want to make sure we understand is the reason that we have the possibility of having spirals and having circles or ellipses as phase plane trajectories is because we don't have eigenvectors, right? Remember, if you have a real eigenvector, which we don't have here, the real eigenvector is a straight line solution in the phase plane. So if you look at an example like example 2 that I have here, this one's going to give me real eigenvectors. And you can see immediately what happens there. Is a very different kind of phase plane. So you've got the point here that travels along this vector, the point here that travels along this one, but you've got two eigenvectors on this problem. I can tell you what they are. Well, how about we say what they are? We know how to do this. So we're almost finished here. The 2x2 system matrix here would be -1, 3, 5, and -3. And we know if we click on that and select eigenvalues, we can select the eigenvectors. So I know I've got two eigenvectors, 1, 1, and -3/5 and 1. So let me just go ahead and put those points in. If I do x of 0 is 1, y of 0 is 1, and add that to the list, you can see that that starts on this eigenvector line and just continues on. So I'll make time go in both directions here so it fills it out. Right, so that gives me the eigenvector. And then the other one is negative 3/5 and negative 3/5 and 1. This will give me a solution along the other eigenvector. So I've got one eigenvector here, one real eigenvector there. I've got the other real eigenvector there. Let me change those colors real quick. So you can see that the orange solution is the one that starts out on x of 0 equal negative 3/5, y of 0 equal to 1. So it draws in that. I'd have to flip the negative and the positive. I'd have to make this positive and this negative to get the other half drawn in. But those are your half-line solutions. Because there's an eigenvector, a real eigenvector in the plane, solutions can't cross through that. So there's no chance with a real eigenvalue of you getting a spiral, because if there's a straight line solution, you can't spiral through a real eigenvector that's straight line. What is the first? Oh, that's not a vector at the beginning here, Madison. Those are the eigenvalues. So the eigenvalue 2 corresponds to the eigenvector 1, 1. And the eigenvalue negative 6 corresponds to the eigenvector negative 3/5 and 1. I have a video up for eigenvalues and eigenvectors in Maple that I did for the, if you go look at the Maple Lab lecture stuff. But these are the eigenvalues for this system. One real, both of them are real, but one's positive, one's negative, and these are the associated eigenvectors. But the point I wanted to make, this is a saddle behavior, by the way, because your real eigenvalues are different in sign. One's positive, one's negative. But the point I wanted to make is you can't get a spiral behavior here, because if there's a half line or full line eigenvector real solution, I can't pass through that because of existence and uniqueness. Remember, solutions never touch. So it's kind of like they're separating off quadrants of the behavior, and what happens in those quadrants is relegated to just that quadrant. You can't get any sort of rotation in the plane if you have a real eigenvector involved. So the only way that we get rotations is if there are no real eigenvectors, and that only happens in the complex eigenvalue case. All right, I know I'm 3 minutes over, so I'm going to go ahead and stop it there, but I wanted you to try to understand why rotations occur in the phase plane for a complex eigenvalue problem. Hopefully we accomplished that today. That should be most of what you need to get started on part of your next Maple Lab assignment, part of your next skills quiz. The remainder of that is the repeated case, and we'll talk about the repeated case on Monday. All right, y'all have a great weekend. If you run into any questions, let me know. If you haven't finished turning in Maple Lab 5, I told you that it would be fine if you wanted to wait till tonight to finish that. Feel free to go ahead and turn that in by later tonight, and have a good weekend.